Linux 2.6. That's pretty some while ago. That's pretty impressive. Since 2012, he has been working on microcontroller-based architectures, focusing on design, development, and integration of software for embedded systems. And with that, the stage is yours.
Thank you. Thank you. Thanks, everyone. I'm Daniele Lacamera, was being introduced pretty fine. And I work for WolfSSL. We honor to co-sponsor the event this year. And today I'm going to talk about one of our products, which is wolfBoot, which is a secure bootloader that aims to provide secure boot and support for reliable and safe firmware updates, and how we integrate that with aerospace systems with our users and customers. So a few words about the company. WolfSSL was born back in 2004. It had a different name. It was called CYSAT. The company, community, MySQL community needed a SSL implementation. OpenSSL was already there, but was too big for the needs at the time, and we aimed to provide a small implementation that would scale better. Initially, it was written in C++. There was a rewrite in 2006 in C, where we switched name to CSSL, and since 2014, we are known as WolfSSL. We have about 2,000 OEM customers, actually, and we secure over 2 billion connections. And everything that we do is dual licensed, GPL and commercial. And the source code is available for downloading both on our website and directly on GitHub. We focus mainly on three main areas, so securing data at rest, so cryptography, SSL TLS, so securing data in transfer, and what we are talking about today, so it's firmware updates, which can be secured with many different application protocols, but most importantly, we will see what the role of a secure bootloader for preventing malicious firmware flashing and unauthorized updates. Quickly, this is our product line. So as you can see, our flagship product on the top left corner is WolfSSL, so the SSL TLS library. And but all the other products, including WolfSSL, will rely on the second item here. It's WolfCrypt, which is our crypto engine. We do have a FIPS 140-2 certification. We applied for a FIPS 140-3, which is upcoming. And we do have the 0178C-A certification for most of the crypto algorithms that are provided with the library. We do also have a few application protocols, but still focusing on security. We do have a TPM library that allows us to interoperate with TPM components, hardware components, and wolfBoot, which is what we're going to talk about today. So what is secure boot for those of you who are not very used to this term, let's say? You want your embedded system to be updated and to normally run only software that can be verified as authentic, so can be verified through cryptography, with strong cryptography, to be generated by a trusted source. So we want to avoid that any adversary could run any non-authentic code on our machine. And this is, of course, a valuable tool for many verticals, not just for aerospace in particular. So the approach of many safety-oriented vertical is sometimes a bit far from what is a normal security guidelines and best practices. So it's important for me to underline the fact that safety never implies automatically security, nor vice versa. So even if you are able to develop top-class safety software, there is no guarantee on security, nor vice versa. So safety code should normally follow cybersecurity guidelines and standards, and we know that. That's why we're here. But also security software must take into account the safety guidelines. And one of the most important things we do for aerospace customers and users is guide and help through the certification of their software products to the DO 178C, which is the guideline for every airborne system, as you probably know. And we follow a few important guidelines when we develop our products. In particular, for this bootloader, we have decided since the beginning, as we will see, not to use any dynamic allocations and to have a predictable execution flow. So everything that the bootloader will do, it can be kind of mapped at compile time without any surprises. We will see how it will go. But another important thing is I hope that we got past the old ancient mentality of if it ain't broken, don't fix it. And we embrace a new paradigm, which is compatible with the vulnerability management guidelines, which means that when something is broken, we should be already prepared to have fixed it. So we need to be able to send updates promptly to our systems, wherever they are, on this planet or elsewhere. So the first thing that came out when we started the design of this 5 years ago, we asked ourselves, is there a standard way to do this? Because at WolfSSL, we don't invent anything. We just implement what's in the standards, right? So standards might be NIST, IETF, or OASIS, or ETSI. But what we do is not original in the sense of the design or the architecture. We follow guidelines that come from the standards. So this is our approach towards TLS and cryptography in general, for sure, because of the NIST requirements. So we try to get the same approach for building this bootloader. At the beginning, we worked based on an internet draft that is called the Firm Update Architecture for Internet of Things, or Software Update for Internet of Things, so from a suite group within IETF. And this was standardized, that's RFC 1919 in April 2021, luckily. Already after 3 years invested actually in this project, so it became an actual RFC. So what does this document specify? The bootloader should be very small, and especially it needs to be agnostic on how the firmware is transferred, because every different application has their own way and their own protocols to transfer the firmware. So we can't bind our user to a specific transport. And especially we need small parsers, because that's what normally is our worst attack surface for secure boot, because of course a secure bootloader requires, as we will see, a manifest header at the beginning which needs to be parsed, and that parser is usually the point where cyber attacks generates from. And the other important thing is that we have to use a secure mechanism which is based on asymmetric cryptography, so public key algorithms, which allows to verify the authenticity. And of course, we make use of digest SHA, in particular for verifying the integrity in the process. So how is wolfBoot designed based on those requirements? As everything we do, or most of the things we do, is written in C, It allows for bare metal use. Of course, it's a bootloader, so there's nothing before us. We need to be usually the first thing that runs on the system. Small footprint, that's definitely a requirement. So wolfBoot is between 10 and 30K in size on a small microcontroller, so it won't use all your flash space. It will hopefully leave some for running your application or your real-time operating system. As I said, we wanted it to be memory safe, so we don't allow mallocs. That's very important because a lot of disasters in embedded start from heap management or heap stack collisions or similar type of mistake that when people say that C is not a safe language, that's what they refer to. We wanted a simple partitioning scheme, especially because flash memories are small and need to be aware of the fact that we need to place multiple partitions in that, and also we need to be portable. So we had an abstraction that would consist in a very, very thin API for HAL to abstract the hardware itself. So we run on many different targets. Bootloader can handle swapping partition, we'll see. We have key tools that can run on the host that allows you to generate, manipulate keys, and sign the firmware as well. Main features here. It, of course, is based on our crypto engine. So by default, it will run with the software cryptography. But we know that WolfCrypt also support many different HSM, and we can also connect it to a TPM or a PKCS11 engine or any crypto provider, let's say. As a public key based root of trust, which is actually more a trust anchor because we just need to guarantee that the public key is never modified. There is support for failure rollback and version protection update. So by default, we only accept bigger version than the one that's running on the target. So we avoid an attacker willing to repeat an older update with an older version in order to exploit a well-known vulnerability in our development history. And we support external flash memories for microcontrollers. Is very important because usually the flash is very small, the internal flash, so we can store the update somewhere else. For instance, SPI or any other NVM that's connected externally that doesn't need to be executed in place because it's just there to store the update. We support, wolfBoot supports updating itself. This is not power fail-safe, but it's an emergency feature in case you discover a vulnerability, even if the code of the bootloader itself is very small. So it is safe to think of a system that has a bootloader, immutable bootloader, maybe even in a ROM instead of in the flash itself. We support encrypted updates. This is an optional feature. And we support delta updates, also an optional feature, but might be relevant if your upload channel is very thin and doesn't have a lot of bandwidth. So you just want to transfer the difference between your current running firmware and the next one. And that comes with double verification. At the beginning, we started on Cortex-M, and then we added many more architectures. We're currently finalizing the work to port to Intel 64-bit architecture as a replacement for SlimBoot. And this is also for one of our aerospace customers that is interested, in fact, on the 0178C and will take the advantage of using wolfBoot with wolfCrypt as a very small footprint, which is also much more convenient and easy to certify for safety regulations for airborne systems. RISC-V, of course, and PowerPC, which is still very much used, especially in automotive. So how does it work with key generation, key management? So the key is generated once on your machine. This is the default use case, but the key generation can also happen externally from wolfBoot because eventually we're just talking about public and private keys in default format, so it's easy. The public key is stored in the target somewhere. Can be a vault, can be anywhere that cannot be written by an attacker. So you can use flash protection, flash write protection, depending on the architecture. You can use other vaults, you can use TPM. And the security will only depend on the private key secrecy, which the private key is normally stored on your backend. So it's in your server. So it never flies or goes to space. It's just there in your office or in your infrastructure. And as soon as that's secret, there is no risk for the process. The sign tool attaches this manifest header, usually about 256 bytes or maybe 512. Depending on the algorithms you decide to use. And this manifest header contains, of course, the signature and the integrity check. So the only requirement that we have is, in fact, this trust anchor that guarantees that the public key cannot be overwritten or modified by an attacker on the target. Of course, yeah, important to mention, the firmware version is also part of the verified payload. So you cannot alter the version and pretend it was a newer version with an old payload, because that would modify the signature and it won't validate anymore. Our boot strategy on microcontrollers relies on the boot update approach. So the firmware update, the firmware always boot from the same place, which is the boot partition. So it's a fixed address. And that's because microcontrollers have physical mapping, and it's not feasible to boot from two different locations. So there we do swapping in place of the two images. On rich systems like x86 or ARM Cortex-A or 64-bit RISC-V, we do an A-B approach. So there is an election or two equivalent partitions after they have been verified. Which one has the biggest version number wins and will be booted, unless you are in a rollback situation. So of course we can't use A/B approach because microcontrollers, because there is physical mapping and the execution in place. So this is an example of a small partitioning on a single MCU case. So we have a small, as we said, 10 to 30 kilobytes partition reserved for the bootloader itself. We have a boot partition that contains the current executing firmware, and that's where your current application is. The update partition will be used by the application to store any update, and if the update is verified, we will use a small swap partition, usually as small as a single sector on the flash, to swap the two images in place. This allows even if the image can be verified, it still can contain bugs that you have inserted. So you can decide a meeting point within your application where you confirm that the update was successful, and maybe this point is a barrier after your system is reachable again or can receive a new update. So you are sure that your system won't break. You don't want to break your system, of course, especially if it's not very easily physically reachable. And that's often the case with satellites, I was told. And so our fail-safe countermeasures, so also known as the $1 million brick avoidance, as having this predictable flow. So we avoid surprises, no heap stack collisions, IRQs are off, and we have a compile time defined behavior. We have a power fail-safe swap, so it means that if power goes down the worst possible point, so when we are swapping the images, basically, nothing happens. The bootloader will just, at the next reboot, resume from where it left off. And the confirm update or rollback to previous version I was talking about. Delta updates, as I anticipated, reduce the update size by creating a binary patch. This still allows reverting because the patch is bidirectional. And we have two levels of authentication there, because first we authenticate the patch, then we apply the patch, and then we authenticate the resulting firmware. So there are two different manifest headers in that case. The one that comes with the patch and the one that's reconstructed from when the patch is applied. And we have worked on the side channel and glitch attacks mitigation. This was a very interesting part of the development of WolfBoot, because your adversary is basically the compiler kicking out your redundant checks there. And we had to work around that to ensure that we could repeat the check. So, because if some attacker is using glitch to skip a specific instruction in your code, in that case, it could be the verification itself. And that's not good, of course. But these countermeasures are strictly architecture specific, so it's not yet available for all architectures, but of course, we are willing to add those as well. Now, the last minutes I have, for me, I will talk a little bit about what kind of problems we already fixed just with the bootloader itself. So we provide a secure and reliable update mechanism, the key management I talked about, detect and discard invalid corrupted firmware, and manage the interaction with the hardware accelerator, etc. This is done through wolfcrypt, and we can have the updates stored in clear text or encrypted in an external storage. What we haven't fixed that yet, just with the bootloader itself, is to prevent firmware update to be intercepted, or ensure that only authorized devices can receive the updates. These are problems that we solve with securing data in transfer. So we have several ways to do that. We of course recommend using TLS, DTLS. TLS and DTLS 1.3 are both supported in WolfSSL. And those are OS agnostic, but also transport agnostic. So we don't need the TCP IP. We can adapt it to any transport data link infrastructure. So we can use DTN with the DTN bundle that's secured, or LTP, or Quick, whatever you think about, we can use. I mean, WolfSSL can run over any transport, just 2 I/O functions, read and write. This is our entire ecosystem. So as you can see, we do have other application protocols that rely on TLS or on the crypto, like the SSH, and we can run over any transport, and of course over any data link protocol. So this will solve the other half of the problem that weren't solved alone by the bootloader. You can have a TLS with mutual TLS and have authentication and encryption of what you're transmitting up to your target. And this concludes my presentation. Thank you very much.
Yeah, thank you very much. Very impressive indeed. Do we have some questions from the audience? Oh yeah, multiple. Wow.
Hi, thank you for your talk. I was wondering if you're going to update crypto algorithms. You say you generate your key once. Does that mean you can't upgrade your crypto algorithms, or is there a special mechanism or something on your to-do list maybe?
Good question. So the crypto algorithm is decided when you first deploy the bootloader, and that's the only algorithm that will be supported in that moment. Of course, wolfBoot supports ECC, RSA, ED25519 and ED448 as public key algorithms, and SHA-2 and SHA-3 with different digest lengths, but you should pick one at the beginning, the algorithm and key size, because this also has an impact on the manifest header length. So a number of things that are decided at compile time in this case. So there is no possibility of upgrading, changing your algorithm unless you use the wolfBoot self-update, which means that you get a new wolfBoot there that's shipped in the same way. So you have to sign the a new compiled bootloader and send it in the update partition. wolfBoot will check in the header it's written that it's ID number 0, which means it's an update for itself, and it will overwrite itself with the new bootloader. And from that moment on, you can use the new algorithms. So I know where this is coming from, and these algorithms will be valid just for a few years starting from now, but we are ready with post-quantum algorithms as well, and we are actually integrating them in wolfBoot while we speak. So there will be a dilithium version of key verification, and at that point, if you upgrade your wolfBoot, you can use post-quantum algorithms as well.
Thank you.
Of course.
All right, wait, another question.
Great, thank you. I thought it was really interesting how you talked about how you're building side channel and glitch attack mitigation into the system. How does that work? Could you talk about some of the architecture-specific checks that you're doing?
Sure, yeah. So basically, it's there is a redundancy of the check that's performed with the volatile assembly. So the compiler doesn't discard that, and it is repeated multiple times. So it is really hard, and this has been validated by our Canadian partner that specializes on this kind of attacks, New AE, and they validated our countermeasures, and it is actually hard to skip a big amount of instructions, while it's quite trivial just with the electromagnetic interference to skip a single line of code. So that's the main point. And then, of course, there are some checks where the order of the operations are also important. So those are also rewritten in assembly. And on top of that, we have a few canaries here and there. So we check the values and their inverse, their complement in rapid succession. So it's easier to detect if one element before or after in the stack has been corrupted, and in that case we invalidate the boot procedure.
Really interesting, thank you.
No problem. But all these are also available on GitHub. If you're curious, you can go and see how I did that. So it's it's some work I'm particularly proud of. It's something. It's one of the most one of the hardest challenges I had to face my entire career. This glitch avoidance.
All right, very cool. And thank you again for your talk.
Thank you.